In the previous part, we talked about the methods to find the rate law expression of a certain given reaction. Method 1 is the log plot. We go to the lab, we did experiments. In one experiment, the concentration of A is negligible with respect to B. In the second experiment, the concentration of B is negligible with respect to the concentration of A. And in one experiment, we calculated the partial order of the reaction M. In the second experiment, we calculated the partial order of the reaction N. Then we can deduce the equilibrium constant K from any set of the kinetic data obtained in reaction 1, in experiment 1, or in experiment 2. The method number 2 was the ratio technique. We did independent experiments of the same reaction. We choose one set of kinetic data from experiment 1 and one set from experiment 2 in such a way, for example, we have the concentration of one reactant is the same, and we divide the rate law expression of set 1 divided by the rate law expression in set 2, and by this way we eliminate, for example, one of the reactants, and we can find the partial order with respect to the second reactant. This is the ratio technique. The method number 3 is the common method, which is the integrated rate law. For any order of the reaction, we have a justified formula. And we studied only the reaction of the type A2 product. For example, if this reaction is of zero order, we justify that AT minus A0 equal minus KT. If of order 1, ln AT minus ln A0 equal minus KT. If the reaction is of order 2, we justify 1 over A minus 1 over A0 equal plus KT. In any kinetic experiment for a certain reaction, we have a table of data, the variation of the concentration of A as a function of time, for example. So we draw A as a function of time if we obtain a straight line. So the formula of the zero order is justified and our reaction is zero order. If not, we pass to the drawing of ln A as a function of time. If we obtain a straight line, the reaction is order. If not, we pass to the variation 1 over A as a function of time, and our reaction is of order 2. We'll pass now to the method number 4, which is indirect method. From the unit of K, we can deduce the order of the reaction. And pay attention, we can deduce directly the global order of the reaction and not the partial orders. For example, for the reaction of order 0, the rate law expression can be written as R equal K. And the integrated law is R is AT minus A0 equal minus KT is equal to the concentrations divided by time. And the concentrations are given in molar, capital M, in mole per liter, molar equal mole per liter, per time divided by the time. So if the unit of K is given as molar, that means this relation is justified, so the reaction is zero order. For order 1, we can write R equal K A. So ln AT equal ln A0 minus KT. This is the integrated rate law for reaction of order 1. So K is ln divided by N is unitless. So the unit of K is time minus 1. if the unit of K is given in the exercise in time minus 1, in second minus 1, in minute minus 1, or in hour minus 1. So this relation is justified and our reaction is of order 1. For reaction of order 0, the integrated rate law justified is 1 over AT equal 1 over A0 plus KT. So the unit of K is 1 over concentration, so 1 over M per time. So 1 over molar per time. If the unit of K is M minus 1, time minus 1, so this relation is justified and the reaction is of second order. So the unit of K is very important in the kinetic. And remember that the equilibrium constant in thermodynamics is unitless. So we are interested only about the units of K, of small k. According to the type of the unit, we can deduce directly the global order of the reaction, but not the partial orders. Suppose our reaction is in the gas phase, so we can pass from the concentration to the pressure, and the pressure, the number of moles, and the temperature of a gas are related according to the ideal gas equation PV equal N RT. So P divided by RT equal V divided by equal N divided by V. E divided by RT equal N over V, and N over V is the concentration. So for gas we can write PV equal N RT, or we can write the pressure, the concentration of the gas is equal to the partial pressure of the gas divided by RT. If the temperature is constant, so the concentration is directly related to the pressure. So what would be the relations, the integrated rate law according to the concentration, if form the concentration to the pressures? For reaction of order 0, AT equal A0 minus KT, instead of AT, we put the pressure of A at time t, the partial pressure of A at time t divided by RT, minus the partial pressure of A at t equals 0 initial divided by RT equal minus KT. So PAT equal PA0 minus KTRT. Look to this relation according to the pressure. It's practically the same relation according to the concentration, but pay attention that K is multiplied by the ideal gas constant R and the temperature T. For the relation ln AT equal ln A0 minus KT, we can write ln AT minus ln A0 is ln AT divided by A0 equal minus KT. So ln PA divided by RT divided by PA0 divided by RT equal minus KT. So we cancel RT and we obtain ln PAT equal ln PA0 minus KT. Exactly, we have the same form as the integrated rate law according to the concentration. So if the reaction of zero order, we can write the concentration as a function of time and So if the reaction is of zero order, we can study the variation of the concentration as a function of time, and we should obtain a straight line. And we can study the variation of the pressure as a function of time, and we should obtain a straight line. So these are the relations of the integrated rate law according to the pressure. Instead, using concentration, we can use the partial pressure of A. Another remark, when the reaction is the form A2 product, the variation of the integrated rate law depends on the order. Suppose the reaction is zero order, so we can write AT minus A0 equal minus KT. Suppose the reaction is not in the form A2 product. Suppose the reaction is in the form AA2 product. The stoichiometric coefficient of A is not equal to 1, is equal to A. So you did the same integrated rate law, but you have to pay attention that in this case, K should be multiplied by the stoichiometric coefficient of A. So for the reaction AA2 product, the reaction, if the reaction is of zero order, so AT minus A0 equal minus the stoichiometric coefficient of A times KT. Pay attention that for A2 product, K is multiplied by 1 in the integrated rate law. For AA2 product, K is multiplied by the stoichiometric coefficient of A, which is the small a. Example 7.5. The reaction SO2Cl2 to SO2 gas plus Cl2 is a reaction of first order. The rate constant is given at certain conditions. Find the concentration of SO2Cl2 at 865 second when SO2Cl2 initial is equal 0.0225. So given SO2Cl2 initial, the time T, K, and we want to calculate SO2Cl2 at time 865. So since the reaction is of first order, we apply directly the relation ln AT equal ln A0 plus ln A0 minus KT. Ln AT equal minus ln A0 minus KT. We have to put minus before minus KT. And we have the concentration initial. So we apply at that time T what is the concentration of SO2Cl2. We will solve this type of exercises in the next session. Half-life. So now till now we have four methods. We have four methods to find the partial orders or the global order of the reaction. We pass to the indirect method 5, which is the half-life. First, I have to define what is the half-life or half-time. The half-life or half-time noted T-half of a reaction is the time required for the concentration of the limiting reagent. Pay attention of the limiting reagent to fall to 1/2 of its initial value, or we can write it as the time needed to form the half of the final product. So if the initial concentration is 1 molar, the time needed to convert the half of this concentration to convert to 0.5 molar, the time needed is T half of this reaction. The T-half expression defines the dependence of the half-life on the rate constant and initial concentration, and T-half is different for different reaction orders. So now, how to use T-half in order to know the partial orders or the global orders of the reaction? First, we have to find the formula of T-half for each order. For order 0, what is T-half? For order 1, for order 2. And we will see that T-half depends on two factors. It depends on the initial concentration, and it depends on the rate constant K. Now, from this formula, we will obtain a formula for order 0, a formula for order 1, another formula for order 2. According to the formula we found of T-half, we can deduce the global order of the reaction. So what is the relation of T-half for a reaction of 0 order? By definition, T-half is the time needed to convert the half of the initial. So at the time T-half, the concentration of A remained at T-half is equal to A0 divided by 2 if we convert the half of A0. So the remain is the other half of A0. So at T-half, the concentration of A is equal to concentration A0 divided by 2. For a reaction of 0 order, the relation AT minus A0 equal minus KT is justified at any time. This relation can be used at any time T. One of these times is the half time. So I will apply this relation at T equal T-half. So AT half minus A0 equal minus KT half. AT half is equal A0 divided by 2 minus A0 equal minus KT half. So minus A0 divided by 2 equal minus KT half. So T half is equal to A0 divided by 2K. What is the conclusion? For a reaction of 0 order, T half depends on the initial concentration of A we start with, and it depends on the rate constant of the reaction. But remember that T half is directly proportional to A0. Suppose you have a reaction, you did several experiments of the same reaction. In the first, you start by A0. In the second, you start by 2A0. In the third, you start by 3A0. So T half in the first is equal A0 divided by 2K. T half in the second is equal to A0 divided by 2K. So we will observe, if we observe that changing the initial concentration of A, T half increase, so T half is directly proportional to A0 and the reaction is 0 order. In the second order, we will observe that T half is inversely proportional to the initial concentration. I pass to reaction order 1. T half is the time needed to convert the half of the initial. At T half, A concentration equal A0 divided by 2. If the reaction we suppose is of first order, so ln AT minus ln A0 equal minus KT is justified. So ln AT half minus 1 minus ln A0 equal minus KT half. Since this relation can be applied at any time T, and one of these times is T half, so ln A0 divided by 2 minus ln A0 equal minus KT half. Ln A0 divided by 2 divided by A0 equal minus KT half, and we observe that T half equal ln 2 over K. And pay attention, in the expression of T half, we observe that we have only the K dependence. For a reaction of order 1, T half is independent of the initial concentration. T half depends only on the rate constant of the reaction, and T half is inversely proportional to K. In order 1, in order 0, T half is directly proportional to A0 divided by 2K. In order 1, T half is independent of A0. T half is equal to ln 2 divided by K, and this is the formula we obtain when we study the radioactive decay in physics. For a second order reaction, we follow the same steps. 1 over AT equal 1 over A0 plus KT. This relation is justified at any time T. One of these times is T equal T half. We put AT by its value and A0, and we obtain T half is equal 1 over KA0. And pay attention, in the expression of T half for a reaction of second order, T half is inverse proportional to A0. So now we have three relations of T half for according to the order. For order 0, T half is equal A0 divided by 2K. For order 1, T half is independent of the initial concentration, equal ln 2 over K equals 0.693 divided by K. For reaction of order 2, T half is inversely proportional to the initial concentration, equal 1 over Ka0. So in your experiment for the same reaction, you can find T half in each experiment. If you observe that your T half increase by increasing the initial concentration of A, so your reaction is of 0 order. If you observe that your T half in the two experiments is independent of the initial concentration, so your reaction is of order 1. And if you observe that T half is inversely proportional to the initial concentration, so the global order is 2. This is a summary of all methods used in order to find the partial order and the global order. For order 0, what is the rate law? What is the unit of K? What is the integrated rate law? The variation of A as a function of time, and T half. So this table is very important. Example 7.6, iodine dissociates at 6 to 5 with a first order constant equal 0.271. What is the half-life of this reaction? Since the reaction is of first order, that means T half is independent of the initial concentration, and T half is given by the relation T half equal ln 2 over K. K is given 0.271, so we divide ln 2 divided by 0.271 second minus 1, and we obtain T half in second. Pay attention, in the chemical kinetic, the unit of the rate constant should be given exactly. What is this unit?